Hi there, and welcome to Unit 14 on Astronomy. I'm Mr. Orr. We are going to be looking at a few things in this lecture, namely the different structures found within the solar system and beyond, and some of the planets and other celestial objects you can find throughout space. So let's get started. First, we need to think about how the universe is organized. So the largest kind of body of organization is called a galaxy. It's a collection of dust, stars, and gas bound by gravity. We'll talk about a few different kinds of galaxies in a moment. The solar system is the next kind of largest denomination. It includes the sun, Earth, and other planets, and a lot of other smaller objects. Sometimes dozens and dozens or millions of asteroids, and additionally some comets as well that revolve around the sun. The solar system is part of a galaxy, so the galaxy contains the solar system. So the solar system is found within it. We live in the Milky Way galaxy. You probably know the Milky Way galaxy is kind of a medium-sized galaxy, and it's a spiral galaxy, as we'll look at in a moment here. The nearest part of the universe to the Earth is our solar system. So our kind of neighborhood in the universe is our solar system. So how did this whole thing start? So the theory is currently known as the Big Bang Theory. And note that it is a theory. It's not a law. It's not something kind of proven to be fact. It's still a theory. So essentially it comes from this idea that all matter was compressed into a single point, like a single kind of dot, about 15 billion years ago. And then at that point, that's where the bang happened, this expansion happened, and that single point of matter expanded out into all the matter we see today. It didn't obviously look like it does today, but it kind of expanded out from that point. Now, it's not really actually an explosion. This is kind of a conceptual model we've created to help people wrap their heads around it. It's more like I guess an expansion is a better thing. Explosion makes you think of heat, makes you think of something combusting or exploding, and it's not exactly what happened. Rather, it was more just a single super dense space, a little tiny dot, and it's been expanding outwards since then, slowly. So as I said, there's three types of galaxies. The spiral galaxy, which has arms of gas, stars, and dust. You can kind of see those arms expanding outward like that. So the Milky Way galaxy is a spiral galaxy. It kind of spirals around that central kind of cluster of stars in the middle. An elliptical galaxy has spheres, or it kind of looks like a sphere. An egg, it doesn't really have those kind of arms. It's sort of all one dense spot. And the irregular galaxy, where you have these sort of indefinite shape, and they're kind of much smaller and more rare than the other two. And this kind of fact down here, which I found and added, there is this instance where galaxies kind of collide and cannibalize one another. They don't actually eat each other, but they kind of incorporate one galaxy into another, which I thought was pretty cool. In our solar system, some more details about that. To be considered a solar system, everything has to have a sun, right? It has to have that central sol, right? That's what the word solar system comes from. Sol is Latin for sun. So you have to have a central sun and other objects orbiting around it. And in our solar system, we've got 8 planets and satellites like moons and other smaller things that orbit around that sun. So a solar system is defined by a sun and everything else that orbits around it. Our solar system formed about 4.6 billion years ago, kind of a similar time as when our Earth started to form, as you should remember. The planets. We're not going to go into a ton of detail on the planets in this presentation. I could probably do a whole, lecture or two on the planets. I kind of find them super interesting, but we're going to kind of do like a quick run through here. So the word planet actually comes from the Greek word for wanderer, and they are the largest objects that revolve around a star. Not every star has planets that revolve around it, but most do. Ours is kind of a typical sized group of planets. We have a bunch of different kinds. We've got rocky planets, such as, let's see here, such as Mercury and Earth and Mars. And we've got some gaseous gas giants like Saturn and Jupiter, Uranus and Neptune. And yes, you say Uranus, not the other pronunciation. Um, there used to be 9 planets, right, until about 10 years ago when Pluto got kicked out of the club. So some more information about the planets. We have inner planets and outer planets. So the inner planets are Mercury, Venus, Earth, and Mars. Those are all rocky planets. They're relatively smaller. Venus and Earth are pretty close in size, followed by Mars, which is a little smaller. Mercury is a lot smaller. And obviously, if you didn't notice this, they go in order from the sun. So like if the sun is here, we're going out in order in terms of distance from the sun. So the Earth is the third rock from the sun, it's known as. A nice distance for supporting life, and we're lucky to be where we are. As I said, they don't have many moons. Earth only has the one moon, Mars has none, and Venus has none. I think Mercury might have a little one. The outer planets are much larger. Jupiter, Saturn, Uranus, and Neptune are huge, right? They're mostly gaseous, ringed, and have many moons. You think maybe you heard me in class say that Jupiter has 61 moons, which is wild. Some of those moons are pretty famous. Titan, Europa. Actually, Europa is Saturn. Excuse me. But these moons are large because Saturn is large. Jupiter and Saturn are both very, very large. Pluto is a dwarf planet. It is not considered a planet anymore. We put it on here just because it's got a really irregular orbit. We'll talk about orbits. We have talked about orbits before. So most orbits, as we'll see later, had this elliptical shape. Pluto's, which is teeny way out here, has this really weird shape, which kind of made it a little too unpredictable to be considered a planet. It's quite small too, which kind of kicked it out from the club. Asteroids are small rocky bodies that orbit close to the sun. Most are found between the asteroid belt in between Mars and Jupiter, and they're thought to be kind of the leftovers, the sort of extra minerals and rock and things like that originated from the creation of our solar system. And some are tiny, like a pebble. It's still considered an asteroid, even though it's tiny, all the way up to something as large as 1,000 kilometers, right? Which would be, from Rochester to, let's say, the edge of Ohio. So that can be pretty darn big. And there's a picture of one there. Now, meteors or meteoroids are actually 3 different things. A meteoroid is a solid debris from space that's moving toward Earth. So this motion here, you guys can see it's kind of showing a motion here. If it's moving toward Earth, it's considered a meteoroid. A meteor is a meteoroid that has entered Earth's atmosphere and is moving at high speed. So as soon as it enters the atmosphere, it turns from a meteoroid to meteor. And then a meteorite, which is another definition here, is what we call it once it's reached the Earth's surface. Once it's crashed and once it's kind of settled on the Earth's surface, it is now a meteorite. We found meteorites. We've got really, really old ones. They're usually like a really, really heavy metal or rock. And it's pretty cool to think about that. They've traveled across the solar system to get to our planet. You maybe have heard of the dinosaurs going extinct. One of these large objects is what's crashed into the Earth and caused that. Okay, moving on. A comet. A comet is another celestial object, so it's really just a quite small body of ice and dust. It's known as a dirty snowball a lot, that orbits the sun. So, if you've got the sun here, comets follow that same kind of elliptical shape that other objects do, right? And they kind of travel around in their orbit. That's why we see comets every so often. So Halley's Comet is the most famous example I can think of. And this comet it comes, I believe, every 75 to 76 years. So it'll come again, not too long. I think it's in another 30 or 40 years. And it travels in this long orbit around the sun, and it passes by the Earth, I should say, every 75 years. So we can see it again in our lifetimes, hopefully. It's got a head and a tail, and the tail is always pointing away from the sun. So it's that kind of trailing thing you can see here. That's the tail. So the tail is there, and that's the head there. So when we measure objects in the solar system, or actually in the universe, it's a big place, right? So we want to use kind of metrics that make sense. So the speed of light is most often used to measure distances. So light travels fast, all right, about 300 million meters per second. In a year, light can travel, I'm not even going to try to attempt to give you the zeros there, but a long distance. Okay, that's known as a light year. So that's about. Let's add our zeros now. 1, 2, 3, 4, 5, 6, 7, 12. Okay, so that's 94 the quadrillion kilometers. So light can travel quite far in a year. Okay, that's why we call it a light year. So that's actually a unit of distance, that light year. So it's just how far light can travel in a year. And aside from the sun, the next closest star, so Alpha Centauri, I believe it's 4.2 light years away. So it would take a beam of light. If I took a flashlight and shined it out into the sun, it would take 4 years for that beam of light, over 4 years for that beam of light to reach Alpha Centauri going at that speed. So it gives you an idea just how kind of far away we are in the universe. There are a few laws that we use to think about objects moving in the universe. 3 of these laws are from a gentleman named Johannes Kepler, probably one of the most famous kind of early planetary scientists or astronomers, really, that we have. So Johannes Kepler, his first law is called the law of ellipses. So an ellipse, if you don't know, if you took a circle and you kind of squish that circle, an ellipse looks like that. If you guys are in doing any pre-calc, at some point you'll start to learn about how you can kind of calculate these ellipses with some calculus. But what they really are kind of a common path that objects take. So the law of ellipses states that each planet orbits the sun in a path called an ellipse, not a circle. So it's a closed curve. So think about a curve that just has a closed end and another closed end, determined by 2 points or foci. So there's one there and one there. Okay. So in a planetary orbit, in the basically the pattern that planets follow, one focus is always located within the sun, and elliptical orbits vary in shape. So the sun sort of determines that the elliptical foci. The second law is a law of equal areas. Now this one sounds kind of confusing, but it's pretty simple to understand. It describes the speed at which objects travel at different points in their orbit. It states that equal areas are covered in equal amounts of time as an object orbits the sun. So when an object is near the sun, it moves fast. When an object is far from the sun, it moves relatively slowly. So this was actually proven by Einstein in his theory of relativity a bit, but it kind of governs how we move through one solar system for one great distance in the universe, or as we get closer to larger objects like suns, our speed increases. And finally, the last one is the law of periods. An orbital period is the time required for a body to complete a single orbit, right? So if I drew an orbit, there's the sun that's going around, to get from point X around back to point X would be an orbital period. So the law of periods describes the relationship between the average distance of a planet from the sun and the orbital period of that planet. So generally what this kind of describes and explains is why the orbital period for a planet close to the sun, like the Earth, is so much shorter than the orbital period for a planet like Jupiter, or a planet like Neptune. So Neptune's year, right, their time it takes to go around the sun is a degree of magnitude greater than our orbital period, mainly because its distance is greater, right? So it explains why the years are so much longer in a place like Pluto or a place like Neptune. Another sort of seemingly maybe random thing to bring up here is an eclipse. So an eclipse is an event where the shadow of one celestial body falls on another. So where one object is kind of shadowed by another. So shadows cast by the Earth and the Moon have two parts. All right, I'll show you a picture of one in a second. The inner cone-shaped part of the shadow, called the umbra, and the outer part of the shadow, called the penumbra. Okay, so you can see in this picture here, you can see the umbra here in the solar eclipse. So in the solar eclipse, this occurs when the sun's rays are seemingly blocked out totally by the Earth, excuse me, by the moon. So if I'm standing here on the Earth, and I look out toward the sun, the moon appears to totally block that. We just had a total solar eclipse in 2017, and we'll have parts of the world will have another one this year, but it won't be as widespread. So you can see that the umbra is closer here to the moon. Penumbra is the kind of wider shadow cast by the moon. And in a lunar eclipse, this is where the Earth kind of blocks off the light that the moon would be receiving. The moon appears to be dark, right? So in this case, the penumbra is here at the moon because it's being cast by the Earth here. You can see the shadow here being caused by the Earth, and this makes the moon appear to be dark. So what you can kind of see here is what would be lighter here gets darkened by the umbra in each case. Okay. All right. So that's it for the lecture. I tried to make it kind of as quick as I could. This is a huge topic. This is a whole course sometimes. Not just a unit. So we've got one more of these chapters to go. It's going to get a little more intense when we talk about how stars form and talking about the different forms of stars. So I try to start you off pretty easy here, and I hope you enjoyed it and study for your quiz.